So hey guys, welcome back. Today we are going to do one of the most important chapters for JE, which is chemical equilibrium. And as you can see that we are going to complete the whole topic here. So I'm gonna be quick. We don't want to waste any more time. So let's get into it. First of all, I'm gonna start with some definitions, uh, which include. So let me quickly open my notebook here. Okay, so just a second, guys. Yeah, now. So before we begin, I'm gonna tell you more about some what is chemical reaction. So it's that some chemical compounds, some chemical reactants react to give some chemical products. So it is basically a chemical reaction. Now, on the basis of completion of reaction, it is completed, it is classified into two categories: reversible and irreversible reaction. So, reversible reaction can proceed in either ways, which means that it can either go forward or backward. So, which basically means that reactants react to give products, but in reversible reaction, the products combine to give reactants back. So, it is reversible reaction, as the name suggests, reversible, which can be reversed, and irreversible, which is opposite of reversible reaction. So once the reactants react and they form product, then products cannot react to give reactants back. Now, reversible reaction equilibrium. Okay, and what do I mean by equilibrium? That the rate of forward reaction becomes equal to the rate of backward reaction. So I'm gonna spend some time here and explain in some explanation that what do I mean by rate of forward reaction. So when reactants react, so let me take an example. Okay, so here we got a basic example, which is that hydrogen plus iodine gives HI. Now these are called reactants, as you have known. These are very basic things. Okay, so these are reactants, and this is the product here. Product. Now, for a chemical reaction, it is basically denoted by, suppose we have this reaction HCl plus NaOH gives NaCl plus H2O. As you can see, this chemical reaction is represented by this arrow, but for reversible reaction we use this arrow, which which basically means that these reacts to give this, and these react to give this. So it is interchangeable. Okay, now these are reactants and these are product. So the rate at which the reactants react, mean they react among themselves. So the rate of reacting is called rate of forward reaction. And when products react to give reactants, so the rate at which the product reacts, it is called rate of backward reaction. Okay, so this is what it meant. Okay, so reversible reactions goes for equilibrium, they goes for completion. They never go for completion, my bad. So reversible reaction attains equilibrium and they never go for completion, while for irreversible reaction they go for completion and they do not attain equilibrium. So some examples are here. So gaseous reactions in closed containers, There are two reactions. For irreversible reactions, as you can see, precipitation reaction, neutralization reaction, gaseous reaction in open container. So chemical equilibrium, what is it? So this is the definition. Chemical equilibrium is a state of reversible chemical reaction at which composition of reaction mixture does not change with time at constant temperature. So let me explain this, and what it meant that only reversible reactions can attain equilibrium, okay, and the composition of the reactant, okay, does not change with time. So this point is quite crucial. So the composition of reactant, I mean, it stays constant with time. I mean, they have reacted and they have attained equilibrium. Now they are, the rate of forward and the rate of backward reaction becomes equal. So no more reactions gonna take place. No more the reactants not gonna not react to give product. So the concentration of the reactants becomes constant with time at constant temperature. So this is a necessary condition at constant temperature. So this is what this definition means. Now moving on to characteristics of chemical equilibrium. So what is it? Let's see. It is a state of reversible reaction. As I have told you earlier, it can be achieved from either side, either from the product side or either from the reactant side. So basically, the equilibrium graph is represented in this manner. So as you can see, this is the concentration. This curve represents the concentration of Hi with time. So this y-axis is concentration and this x-axis is time. This the middle curve represents the H2 and the upper one represents I2. As you can see that this is the equilibrium state, this line. After this they become all parallel. They become parallel, so they have achieved equilibrium state. Okay, yeah. Moving further. So here's a quick question. Do it. Okay, so let me show you the question. It's complete the following. PCl5 PCl3 gives PCl3 plus Cl2. 5 moles 0 0, 3 moles 2 2. So this is the graph. Okay, yeah. So as you can see, the initial concentration for the products were 0 0 and 0. So they went to 2 when the reaction is completed. Then they have attained the equilibrium state. Similarly, initially the PCl5 has a concentration of 5 moles, but it reacted and the final concentration left as 3 moles, so it decreased. As you can see, there's a downward curve here. So they both reached equilibrium at the same time. So as you can see, these are at same line. These 2 points lies at same line, which represents some time t. Okay, so here are some few more questions. Do it for yourself. I'm just showing, take screenshots. Okay, so in equilibrium state, the rate of uh, forward reaction is equal to rate of backward reaction. It is dynamic in nature. It is not static, it is dynamic. At equilibrium, delta G is equal to 0. Delta G represents Gibbs free energy, delta S represents system energy of the system. Okay, now we have law of mass action. According to this law, rate at which a substance reacts is statically proportional to the active mass of substance. Active mass in aqueous medium is molarity. You guys have to remember this, that active mass of a substance in aqueous medium is molarity. It is calculated by molarity. Active mass in gaseous phase, it's molarity or partial pressure. generally we use partial pressure and we use molarity very less, and even in questions you'll encounter partial pressure more as opposed to molarity. So for aqueous medium it's molarity, for gaseous phase it's partial pressure, and for uh, and for active mass in terms of molarity it can be represented as number of moles by volume in liter. So um, now we're gonna try to see how we can write the equilibrium constant. So I'm gonna take an example here. Let's say that A plus B reacts to give C plus D. We're gonna take some stoichiometric coefficients, okay? So let it be A, B, small c, small d. So for this particular reaction, if you have to write the chemical equilibrium constant, then it's this generally represented by Kc, which is equal to concentration of C raised to power this concentrate into concentration of D raised to power this by concentration of A. So generally we for a substance, for a chemical compound, we represent its concentration by big brackets. So we generally write the, suppose for NaCl, if we have to represent its concentration, so we just put it in the big brackets, okay? So this is what it represents. It represents concentration of C and concentration of D. So this becomes raised to power A and concentration of B raised to power B. So this is the chemical equilibrium rate constant, and you have to remember it. There's no other way. So yeah. Now one more thing. Sometimes when gases are given in reactions, then you have to work not in concentration but in partial pressure. As I have told you earlier about this, that you have to remember active mass in aqueous medium is expressed in terms of molarity, while active mass in gaseous phase is represented in terms of partial pressure. So if partial pressure is given, then you have to take that same, let's see, Kp is equal to PC. Suppose the partial pressure is PC, PD, PA, PB. So this is the reaction, okay? We are writing the chemical equilibrium constant in terms of partial pressure. PC raised to power into PD raised to power D by PA raised to power A into PB raised to power B. You have to remember it, okay? It can be expressed in terms of mole fraction, which is nothing but so yeah. Now active mass of solid is 1 and active mass of pure liquid is 1. So as you can see, here it is. Now chemical equilibrium, homogeneous and heterogeneous. So for liquid phase, we gonna generally represent the chemical equilibrium in terms of molarity, while for gaseous phase we're gonna represent it in terms of partial pressure as well as molarity. So here are some questions, we're gonna skip it. So we can find a relation between equilibrium constant, that is Kc and Kp. So let's say that we are taking this as our example. This is in gaseous phase. Okay, so all these are in gaseous phase. So we're gonna write that chemical equilibrium in terms of partial pressure, Pc raised to power C, PD raised to power D by PA raised to power A, PB raised to power B. But we also know that the ideal gaseous equation, which is nothing else but PV is equal to nRT. We all know that this, right? So using this, we can write PA for A is equal to NA. It is same for everyone. R is universal gas constant while temperature remains constant for this whole reaction. So this remains same for each one of them by V. So as you can see, this is nothing else but molarity. So it's basically concentration. So we can write it as PA, and I have told you how we represent concentration by writing the name of compound in big brackets times RT. So similarly, we can write PB as concentration of BRT, PC as concentration of CRT, PD as concentration of DRT. So we're gonna substitute the values here in this equation. We get Kp is equal to concentration of CRT raised to power C, concentration of DRT raised to power D, concentration of ART raised to power A, concentration of BRT raised to power B. Now this becomes Kp is equal to concentration of C raised to power C, D this, A this, B this, RT, C plus D minus A plus B. So this is nothing else but Kc. So Kp is equal to Kc RT delta Ng, where delta Ng is equal to C plus D minus A plus B, or this can be written as summation of moles of product minus summation of moles of reactant. Okay, delta Ng. So this is the relation you have to remember it. So before we move further ahead, similarly you can derive a relation for mole fraction. Okay, so here's the derivation for it. So P here is the total pressure. We know that for mole fraction what we do is, for suppose there are 4 compounds A, B, C, D, total moles is N, and the individual moles is Na, Nb, Nc, Nd. So the mole fraction of A is Xa. It is represented by X, Na by N. So this is the mole fraction. Similarly, for in terms of partial pressure, this can be Pa by P, or Pa can be written as Pxa. So this is what it is done here. Similarly, Kp can be written as this, and here it was RT here, and here it comes as P. So that's the only difference. Just remember it. Okay, just remember this. Kp is equal to Kxp delta Hg. Remember it. So there are some factors affecting equilibrium constant. Equilibrium constant K is independent of concentration, yeah, of reactant and partial pressure of reactant product. Bye, guys.